All right, students, welcome to your AP Unit 5 pre-lecture on chemical energy. We're going to turn from integrated rate law and we're going to start looking at the role of energy and how we understand why reactions occur at the rate and via the mechanism that they do. So as you notice, this is a little bit different. Today in 2023, our Wi-Fi is almost completely out and we're having a lot of troubles connecting. So I will be doing this through typing. But on the plus side, these notes are very much non-drawing related. So this should just be a little change. So go ahead and get out your notes and follow along with me. So first and foremost, chemical energy, okay, is understood as a type of potential energy stored in the chemical bonds. Potential energy is energy due to the position or placement of your particles, right, or of your object. So what we're really thinking about is it's the energy due to the particular bond arrangement of the atoms, right? So how they're bonded is a way to, in space, arrange them and give them a unique value of energy that could potentially be used to do something else, okay? And we also call the chemical energy stored in bonds, we also call it bond energy, okay? So to make it really even more clear and even more refined is that it's in particular the positioning of the electrons in one atom relative to its own nuclei or nucleus or whatever nucleus, I think nucleus because it's single, and in relation to the other bonded atoms nucleus that creates an energetic tension, i.e. the potential energy. So energy conversion wise, we should remember the law of conservation of energy. That tells us that energy can neither be created nor destroyed, but can be transformed. So what does that mean for us in chemistry? That the chemical energy is often converted, chemical energy stored in the bonds is often converted to heat or kinetic energy throughout a chemical process. Okay. And this heat energy is released, okay, or absorbed. All right. So enthalpy is the particular term that we use in chemistry, with symbolized by H. Okay, enthalpy representing the heat. Okay, symbolized by H is the potential energy that may be evolved, i.e. released, or absorbed as heat within a chemical process or system. Okay, so that's just the technical terminology for it all. And why do we like this? Oh, and by the way, the units for this tend to be in kilojoules per mole. So it is an extrinsic property that is dependent on the amount. And notice it is a derived unit, which means it can become a unit conversion in the future by moles. So we're going to eventually tie this in with stoichiometry. Okay, so things to look forward to. Okay, so what's its usefulness? Well, when we discuss the change in enthalpy, triangle change in enthalpy, we can track okay, the chemical mechanism. We can basically outline or track/outline the chemical mechanism of a reaction by measuring the changes in energy, because they indicate changes in bond arrangement or atom arrangement, right? So when you look at this, and I'm trying to make it so it fits. Okay, so when you look at your potential energy curves versus internuclear distance, right? Something that you might notice is that bond breaking, i.e. the reactants reacting, right, colliding, requires, right, an input of energy, i.e. absorption, right? But bond forming, okay, would require, bond forming, i.e. the formation of the products, what's happening in the products, require, or I don't know about actually require is the right word, involves the release of energy as it is stabilizing, right? So of course, we've looked at these internuclear graphs before, and we said to ourselves, yeah, that makes sense, because at the ideal bond length, we see that the potential energy is the lowest, therefore showing that we have a release of energy or stabilization. But we also know from our previous discussion on collision theory that it takes energy to collide to indeed have a successful reaction, to initiate, to activate the bond breaking. Okay, it takes a certain amount of input of energy, force, right? So we kind of see this through both a combination of our prior knowledge and the re-examination of this curve. So understanding that, we actually get a couple new pieces of, or I guess you could say new categories or ways to understand a reaction in terms of now energy. We can now mark a reaction as endothermic or exothermic depending on the overall net sum of energy involved during the chemical process. So an endothermic reaction occurs or is categorized when a reaction's overall net energy is absorption throughout the chemical process or the reaction. Okay, so for example, and let me change this to single so we can space it in. For example, we see that energy, let me do this for you, energy required to break the bonds is greater than the energy released in the making of new bonds, is how we understand it from a particulate level. And the key here is to remember that you're still technically releasing energy when you make the new bonds. So you're still forming a stable or more stable, relatively bond arrangement, okay? Which is why endothermic reactions still exist in the world. Because you might think automatically, oh, well, if I'm not having a net release of energy, right? Why would my particles even go through the process? Well, don't forget, it has to go through the activation energy, which is an incredible amount of energy, which we will diagram in class together, and it'll make a little bit more sense. But there's still a relative release of energy that still makes it more favorable than other points throughout the reaction process. But what we see is that when we compare the final states, the initial and final state, we see that our final bond arrangement is still slightly higher in bond energy than our initial bond arrangement, okay? And this is reflected, by the way, when we add a quantitative value, having a change in enthalpy that is positive, all right? So exothermic reactions, on the other hand, occur when your overall net energy is released, okay, or is emitted, or is a type of emission. How do I say that right? is absorption, is emission or releasement. I don't think that's a weird word, or releasement throughout the chemical process. So what we see then is from an understanding that it's at a more particulate level, that the energy required to break the bonds is less than the energy released in the making of new bonds, right? So you're probably already putting together that exothermic reactions will generally, by the way, because of this overall net release, not just a relative release, as exampled in endothermic reactions, but due to this overall net release, okay, net energy emission, net stabilization in an exothermic reaction, you can already probably tell that exothermic reactions tend to be more favored in the universe. But again, we still get both. It's not like it's impossible to get endothermic. In fact, there are several reactions that are totally endothermic and still spontaneous. They are still relatively favored by the universe. And you'll see as we progress in our chemistry understanding other factors that can help explain why that occurs. Okay. But quantitatively, the H value is going to be a negative if we take initial, final minus initial heat or chemical bond energy arrangement and we compare them, we'll see that there's a negative, okay, change in enthalpy or heat energy stored in the chemical bonds when looking at exothermic reactions. So the general equation for calculating the change in enthalpy is the following, that the change in the system, okay, is equal to the potential energy of the products, okay, which is represented in enthalpy values, but particularly to those particularly to those product species, minus the potential energy in the reactants. Okay, and we're gonna kind of parse this out in further detail, but that's the big idea. The intricacies of how we calculate potential energy of products and potential energy of reactions, we're going to splice out later together in class, but this is the big idea. And then of course, if your H is positive, it's going to be an overall endothermic reaction being represented. And if it's negative, it's going to be an exothermic reaction being represented. We're going to, again, delve further into that in Unit 6, but there are two ways that we represent enthalpy, and this is just a notation thing, but the first method is known as a thermochemical equation, okay? So what we say is that we include the heat in the actual chemical equation. So if I have, let's say, A plus B goes to C and it releases energy, exothermic, I would just simply add my energy value into it. Maybe I even write the value, 191.1 kilojoules per mole, okay? I put it in my equation. Likewise, if it was exothermic, okay, I would say, oh, goodness gracious, this is totally exothermic because it's heat as a product. And on the other hand, if this was endothermic, I would, in the thermochemical equation method, okay, add heat into the reactant side because it's an input. Another way we can do this is called H notation, which I actually find to be more common in the AP, but it is what it is, as long as you can read both. This is where we write the equation and then we separately on the sidelines tell you that the enthalpy is equal to negative, okay, 191.1 kilojoules per mole, representing an exothermic reaction. And for an endothermic reaction, we would again still leave the equation in its own kind of notation, and then we would add on the sidelines the value of enthalpy for the system, but this time representing a positive number for endothermic. These are just two notations that you should be familiar with, able to read, able to write yourself. They say the same things. It's honestly just kind of a matter of preference. So tomorrow we're going to look deeper into activation energy because it's going to help us understand. Oh, actually, just kidding. There's a little bit more. I actually decided I did want to talk about activation energy. So we're just give me 2 more minutes, guys. Um, Imagine a slow motion model of the moment when particles collide to break and form new bonds. All right. So this high energy point, what we say is that an activated complex is formed. And an activated complex is, all right, give me a second. Man, working with no Wi-Fi and no lights is very interesting. Um, what we say is that a high energy and unstable transitional or temporary, right? It's an instantaneous temporary compound, configuration or compound um, of the atoms is formed at collision. Okay. So if you look to your right, what you see here is, let's say I have a reaction between H2 and I2, right? And I know that to break bonds, the process of a reaction occurring is dependent on successful particle collision that meets the activation energy. Again, we are sticking in the terms of energy for understanding how a reaction occurs. Okay. It has to meet the set amount of energy. And let's say it does. The particles collide with enough energy meeting the activation energy and successfully begin the process of breaking bonds. Well, almost immediately as you break the bonds, it would make sense that you would form them while your particles are close together. So it's kind of like an instantaneous, simultaneous bond breaking and bond forming initiated by the split second prior breaking activation portion. I know that's like a lot of words. I'm sorry. But what we say is, when we look at this kind of simultaneous process of bond breaking and bond forming, indicated by the dashed lines in the middle of this sequence in the diagram, we say that we create an activated complex, which itself is the high energy complex that actually is what defines the activation value. This high energy complex is actually what defines our activation value for a given reaction. So, if we were to break this down, what we would say is that the process, if we would break down the process, we say that reactants are breaking their bonds at the same time as products are being formed. Okay. And by that, I mean new bonds, right? So we could also look at it say that the point of the reaction at which the potential energy in the system is max due to the high strain and tension required for breaking. A high strain and tension required for breaking. And lights came back on. That the point of the reaction at which the potential energy in the system is the maximum, high strain and high tension, and when kinetic energy is at a minimum. Okay, is another way of understanding this activated complex, or this state in a reaction that is essentially demonstrating the mechanism of how the particles must successfully collide and the energy required of it. And it also defines, of course, the activation energy that we say gatekeeps or determines, and is incredibly impactful in understanding the rate of a reaction occurring, as well as its likelihood of occurring. So I hope that was a decent summary. I'm kind of working on the fly with the Wi-Fi being out, but we will be going over all of this and activation energy in particular tomorrow with diagrams to help you understand further how it all fits in to the general process of illustrating and describing how a reaction occurs from beginning, reactants, breaking, to end, products forming. All right, guys, really good job. Have a great one.